Rich Hallett and Dr. John Gunn, and then also Nate Torbett is on the line. He's got a child that's got a fever, and so he's having mercy on us and not bringing whatever that is into the building today. So I'm Russ Congleton, for those of you who don't know me. Ben's been at UNH for a long time. He's a homegrown guy. He got his undergraduate degree here in wildlife, and then saw the light and switched to remote sensing. And so he's worked with me on his master's thesis, actually really on the bleeding edge of using UAS technology when we first had permission, and even before we quite had permission to use the sensors on the UAS. And now he's working on his PhD, kind of continuing some of that work and then taking it into new directions. And so we'll hear about that today. So I'm going to turn it over to Ben. We'll have questions at the end, so please feel free to think of your questions, jot them down if you want to, and then we'll let you ask those questions at the end. Then we'll get rid of the general public, and the committee will spend 6 or 7 hours asking Ben questions, and then we'll see what happens after that. So I'll turn it over to you, Ben.
Yeah. So thank you everyone for taking the time to be here this morning despite the very uncertain climate and the fact that it's the Friday morning before spring break.
And it's Friday the 13th.
And it's Friday the 13th. We're lucky
You weren't
here.
supposed to point that
Oh.
out.
Now it's a very unlucky presentation. But I'm very excited to be able to share with you my dissertation research proposal today during this presentation. All of this work that will be discussed has been organized and kind of structured over at least the last 2.5 years since I started in the PhD program. But like I said, I've been here for a lot longer than that, kind of setting up the introduction and having some pilot studies on my master's thesis. The entirety of this research today follows under the heading of my proposal, which is characterizing forest stands using unmanned aerial systems, evaluating forest characteristics and ecological health. This presentation today follows the outline of my proposal. I'll begin with some general background information so that everyone can understand the focus and the importance of this type of research. Then I'll talk more specifically about each of the individual chapters in the research. These are 3 distinct studies, which I'll provide an overview of more specific concepts which are relevant to that type of research, and then discuss the methods that are being proposed to complete that study. At the end of the presentation, just before questions, I'll have a short project overview in which I discuss where the project currently stands and the next steps that are intended to be taken. To begin with the introduction, of course, forest ecosystems provide many goods and services which we rely on as a society. These services can be categorized as regulating, such as the use of timber resources, provisioning, such as nutrient cycling and water quality, or cultural, such as hiking trails and aesthetic green spaces. We're very fortunate here in New England to have a diversity and abundance of forest ecosystems across our landscape. To best understand, measure, and monitor these ecosystems and how they provide us services, we must be able to delineate them into unique community types. These community types can also be thought of as forest cover types or forest stands, the primary definition of which are homogeneous groupings of trees with their associated vegetation and the soil and similar soil and climatic conditions within them. While we rely on these systems for many services, it is becoming increasingly apparent that they are being degraded and altered at both global and local scales. Both natural disturbances, such as forest fires and drought, and human-caused or anthropogenic disturbances, such as land cover change and overharvesting, are causing alarming issues in our current environment. The projections of both of these types of disturbances are all showing that they're going to worsen and have lasting impacts in the coming years. There are many challenges for understanding the current impacts of these disturbances and modeling them into future projections. These challenges include having timely and scale-dependent data and understanding the causes and changes at local scales and being able to interpolate those across larger environments. Both environmental science and conservation are aptly becoming interdisciplinary fields. Now more than ever, programming, computer modeling, and big data are at the forefront of conservation science. Many researchers are aptly and endearingly calling this a shift in eco-informatics. There are 2 fields that have been benefiting this trend for a number of decades now. These include remote sensing, You can think of satellite and aerial imagery, which allow humans to collect data across scales and resolutions far beyond which would be capable with just human senses alone. There's also Geographic Information Systems, or GIS, which allow us to display, manipulate, and analyze spatial data across temporal and varying scales. UAS, or Unmanned Aerial Systems, represent one fascinating culmination of many of these ideals. You've likely heard of unmanned aerial systems discussed by many of their ambiguous names. These are unmanned aerial systems, UAS, UAV, remotely piloted aircraft, drones, or even aerial robotics. Here, through review and use of this platform, we support the term unmanned aerial systems. This is because they do represent a system of interconnected components, such as the ground control station, the radio communications links, the aircraft itself, and of course the human operator, which is always necessary. These platforms have had a long history of primarily military development. We've all heard of Predator drones now, but since before World War II with guided missiles, the technology has really become much more advanced. Thanks to the technological boom at the beginning of the 21st century and the miniaturization of computers, which we now readily use with our cell phones all the time, these platforms have become lightweight, small form factors, and very capable of collecting highly detailed data. Also, thanks to this rapid change in technology, federal and national agencies around the world, such as the Federal Aviation Administration here, has had to try to keep up with the pace of consumer and commercial uses to try to make sure that regulations fit within their wider airspaces. With the diversity of unmanned aerial systems that are now available, we can create high-resolution spatial models using long-established fundamentals in mathematics and photogrammetry. These spatial models are now highly automated in their completion thanks to computer vision algorithms. With the structure for motion process, we can collect optical imagery, regular natural color imagery, with heavy overlap, and then using one of many computer softwares, align those photos in three-dimensional space, extract individual features, distinguishable features within the landscape, and then aerial triangulate them to create a three-dimensional point cloud or network. With the framework of this sparse point cloud, the additional views and viewpoints and textures available in the landscape can then be filled in to form a dense three-dimensional point cloud. With this dense network of three-dimensional points representing the landscape, we can then perform a simple interpolation algorithm to create various products such as a textured mesh or digital surface model, which you see here. And finally, the mosaic of imagery can be geometrically corrected or planimetrically corrected to create a flat surface that removes scene displacements and a lot of lens distortions. What's most powerful about this automated workflow now is that it doesn't require highly sophisticated or calibrated million-dollar cameras like traditional photogrammetry does. Simple point-and-shoot cameras or even your cell phone imagery, if you capture a sufficient number of images from various perspectives, can be used to create highly detailed textured three-dimensional models of the structure which you wish to complete. There are as many applications of unmanned aerial systems as there are modifications. You can see just a short list of those here on the slide. These applications are popping up all over the place as more fields begin to adopt these easy-to-use platforms. We've known now for a while, though, that following other traditional sources of remote sensing, that having a greater amount of data doesn't always answer the questions that we're developing. We need a combination of more data, more effective methods, and better communications of those methods and results in order to understand the diversity that is apparent at our local scales in our natural complex systems. It is for this reason that I hope to complete 3 studies on the use of unmanned aerial systems for evaluating forest characteristics and ecological health. The first of which will be to map species composition at an ecologically and economically relevant scale, the forest stand. Once we've established the species composition of each stand, we will look at the accuracy and precision of estimating key forest inventory variables, in addition to mapping ecologically important large trees in the landscape. For the final chapter, we will determine the ability to monitor and classify forest health of major species groups that are located in our landscape. This first chapter is a continuation of my master's thesis research here on the quantification of reference data collection using unmanned aerial systems. For an introduction to that, thematic mapping, which could be better understood as land cover or land use mapping, has great value for creating representations which can solve spatially oriented environmental problems. The methodology for creating thematic or land cover maps has existed for hundreds of years. You can think of resource-oriented maps or mapping vegetation cover across wide landscapes. But now, thanks to a lot of the developments in various technologies, many of our thematic layers are created through remote sensing imagery or data. There are a number of ways of turning raw remote sensing data into a thematic layer. With modern computing, this is often accomplished through the use of digital image processing and a classification algorithm. Classification algorithms can be distinguished in a number of ways, some of the most distinct of which sort out whether the algorithm works on a pixel-based basis, which is in the upper right-hand image, so each pixel in the image is classified, or whether it works on a pre-segmented object-based methodology. You can also distinguish if the algorithm works with a simple statistical methodology, or if a complex machine learning or artificial intelligence algorithm needs to be applied. Finally, a classification algorithm can be distinguished whether it's supervised or unsupervised, denoting the use of user-inputted training data in a supervised classification. Following the creation of a thematic layer, and before it can be used to support decisions, its accuracy should be sufficiently validated. The accuracy of a thematic layer can be thought of in the context of positional accuracy, or the location of individual features within that layer, which has been classified. Or here, we will focus on thematic accuracy, or the labeling of those individual features. For the quantification of thematic accuracy, we use the error matrix shown here, which is a site-specific comparison of the classified layer to some sort of reference data or established metric for reality. In addition to these concepts of quantifying the accuracy of a layer, it's also important to perform additional explorations of the data throughout its creation and processing so that it can be fully understood what the uncertainty or accuracy of that layer is held to. To validate the accuracy of the thematic layer requires the comparison to some sort of established metric for reality. These are referred to as reference data. During the validation stage, it can be thought of as validation data, but additionally, reference data, due to their rigorous collection, can be used in supervised classifications to train the classification algorithm. Reference data can be collected from a number of methodologies or procedures. These include the use of high-resolution imagery, having a map of known quality to establish it from, or most commonly, and also most costly, having ground-based or field sampling. These data are extremely costly to collect, especially when considering having a valid sample size to perform the accuracy assessment. But it is critical to make sure that the classification algorithm and the resulting product are correctly trained and validated. But because of their sufficient costs and requirements on the projects, they are often not collected, even in modern times, to a sufficient degree. It is for this reason that we intend to investigate the use of unmanned aerial systems for facilitating more efficient and effective reference data collection. During this first study, we will determine the accuracy or agreement of UAS reference data collected among the complex forest here by comparing it to field-based plot inventory data or ground reference data. We will also be comparing this UAS reference data to other traditional sources of reference data collection from remote sensing platforms. Finally, we will investigate the efficiency of collecting unmanned aerial system reference data by computing a minimum effective sample size for classifying a forest stand accurately, which you'll see at the end. For this first chapter, there are 13 woodland properties and over 4,300 acres of land that are going to be mapped. These properties, for these properties, 11 of them are owned and managed by the University of New Hampshire, really located in southern New Hampshire. One of these properties is the Blue Hills Forest, located in Stratford, New Hampshire, and the final property used for this study is the Fox Demonstration and Research Forest in Hillsborough, New Hampshire. All of these locations were chosen because they have available ground reference data already collected, so we don't have to go out there and spend tons of time on that. They also provide spatially contiguous representations of natural forests, which are available in our landscape. And of course, each of the managers of these properties has allowed or permitted unmanned aerial systems research, which we can't say about everywhere else these days. Our classification scheme is a modification of our previous research during the master's thesis, in which we investigated only coniferous, deciduous, and mixed forest cover types. Now we use a modification of many local and recent forest stand classifications, in which we include 3 coniferous, 1 mixed forest, 4 deciduous or hardwood classes, and an other forest class. Here you can see examples of those coniferous, mixed forest, and deciduous classes. We also define a minimum mapping unit for the size of a forest stand, in which we require at least 5 acres in size, and the forest stand must contain a minimum of 3 ground reference or continuous forest inventory plots. The available field inventory data is represented by these continuous field inventory plots. These are long-term research locations which are sampled generally on a 10-year interval. The sampling design of these individual plots is specific to the woodland manager of the property. So all of the UNH properties follow the same design, but Blue Hills and Fox Forest have a slightly different implementation. From these ground inventory plots, there are basic attributes such as species identification, diameter, breast height, and tree location, which can be used to classify or quantify the basal area proportion of each species, which is represented in the landscape. From the classification of these individual plots, forest stands can be delineated by aggregating homogeneous groupings of the classifications, and then using high-resolution imagery and wonderful undergraduate technician, these areas are delineated for more natural boundaries. To best evaluate our unmanned aerial system reference data, we also include traditional sources of remote sensing imagery, which are commonly used in the literature to serve as reference data for larger projects. These include National Agriculture Imaging Program, or NAPE imagery, which was collected in 2018 for most of the state. It has a 60-centimeter spatial resolution and contains 4 bands of spectral information. We've also included the use of Google Earth imagery, which is mosaic imagery, in which we use 2018 and 2019 LEAF-on cloud-free imagery as our source of reference data for interpretation. These individual sample units are represented by the 30 by 30 meter boxes, which you can see in the slide here. And these are distributed to match the locations of the ground reference data plots throughout the landscapes. So for College Woods here, you can see that they are located throughout each of the forest stands, but matching somewhat of a systematic distribution, which was originally intended. To collect reference data using unmanned aerial systems, we will operate 2 primary aircraft, the Sense-Fi EB+, which is pictured here in the presentation, small fixed-wing aircraft, and the newer model, the Sense-Fi EBX, which is located here on the table. Both of these aircraft are able to operate their own specific high-resolution natural color sensor. They are also both able to operate the multispectral Sequoia Plus 5-lens sensor. The flight planning for these aircraft are completely autonomous or pre-programmed. Using a GIS, the forest properties are delineated into rectangular boundaries. We have flight parameters which have been refined over the last 4 or 5 years of flying with these systems, And once we've uploaded that data to the aircraft, you simply turn it on and launch it, and it'll control all of the rest of the image collection process, hopefully landing where you expect it to at the end of the mission.
Not in the tree.
All over the place. The goal of collecting reference data using these aircraft is to collect summertime leaf-on imagery for all of the properties, and then for select or as many properties as possible, we also hope to collect imagery and model fall senescence or fall foliage colors. Once the imagery is collected, it is processed into spatial models using the structure from motion workflow, which is shown in the introduction. The goal of this processing is to create highly detailed and largely artifact-free orthomosaic models for each of the properties. Once these orthomosaics can be created, we have visual interpretation training keys and visual interpretation of the individual units to classify manually the composition of each of those reference data samples. This is completed with the help of a couple of great undergraduate technicians, so that way we can compare their answers and provide one average sufficient classification using the process, which is very similar to what was accomplished in my master's thesis. Additionally, these orthomosaics will be segmented using a computer program called eCognition, in which each of the individual trees will have its boundary delineated and extracted. Once these individual trees can be identified, 3 supervised classification algorithms will be used to classify each tree within the landscape. These classification algorithms include maximum likelihood, random forest, and support vector machine. To quantify the accuracy of each sampling design, both unmanned aerial systems and traditional remote sensing methods will each can be compared to the ground reference data composition. These will be completed using the thematic map accuracy assessment error matrix, which you saw in the introduction, in which we will analyze both the overall accuracy of the classification or the agreement between the methods and the class-specific accuracy or agreement between the classifications. Additionally, the best performing method across all platforms, for example, the support vector machine classification, will be compared across those methodologies using a kappa analysis to determine if they provide statistically different results from what would be expected from random chance. For the final analysis of these classification performance, we will also be investigating the minimum effective sample size required to classify accurately a forest stand. Using linear regression and bootstrap resampling, we will be able to calculate if it requires roughly 4 samples to accurately classify a forest stand of this size, or if in fact you do need 10 or 11 samples to perform that classification accurately. Okay. With the species composition and forest communities defined, we move on to the estimation of forest inventory attributes and community characteristics using unmanned aerial systems. The characterization of forest stands can be accomplished using a number of attributes, either resource-oriented or ecologically minded. These include variables such as basal area, tree density, or stand age. Forest inventory methods, especially in a resource-oriented approach, have existed for hundreds of years, but have refined a lot in the last 100 years or so to be more holistically or ecologically minded. There are many collection agencies for these types of forest inventory data. At a national level, there are federal agencies which collect data such as the Forest Inventory and Analysis dataset. At a more local level, universities and local conservation groups typically set up continuous forest inventory plot networks to monitor long-term basic trends across their landscapes. The attributes collected in these framework typically include species identification, diameter at breast height, sometimes tree to get at volume and stand densities. In addition to these general attributes which are collected during forest inventories, additional community characteristics such as the presence of large trees are important for quantifying the economic and ecological value of forest stands. Large trees, which are regionally defined as those with greater than or equal to 40 centimeters in diameter, provide a disproportionately higher value to forest stands in terms of timber value, carbon storage, biomass, critical wildlife habitat, and nutrient cycling. These types of ecosystem goods and services are provided by living live standing trees, dead standing trees, and down logs. These large trees are also one of the primary characteristics used to define old-growth forests, the other characteristics of which include a diversity of stand structures, having crown closure, and having specific species assemblages based on the region of the forest type. Traditional remote sensing platforms such as satellite and aerial sensors are often used to expand both the extent and resolutions of field methods. But in the context of measuring forest attributes, especially at the local level, lack sufficient spatial, spectral, and temporal scales to perform these estimations accurately. There is a lot of recent literature on the use of unmanned aerial systems for completing forest inventories, and some of them are showing quite prominent results. Many of these techniques are in combination with sensors such as hyperspectral cameras and LiDAR or laser scanners. Many of these studies or projects, however, are missing some combination of optimized and detailed methods, the investigation of complex stand structures, or the study of complex stand compositions. It is for this reason that we also employ the use of unmanned aerial systems to estimate key forest stand biometrics and determine the accuracy by measuring that against that of ground reference or continuous plot inventory data. We will also be assessing the detection of large trees, both standing and dead, to have that additional ecological indicator and economic indicator of forest stands. The study areas included in this research are designated based on the specific objective in which they support. In total, there are 11 properties included here and over 2,700 acres of land. For each of these woodland properties, as it was discussed in Chapter 1, there are continuous forest inventory plot data available to serve as ground reference data. These inventory plots are spatially distributed and have records such as the species ID, the plot or tree location, diameter, breast height, and sometimes tree height and other important variables. These data can be taken to estimate other values such as basal area at the stand or hectare level, stem densities, and also tree density. To create the best comparison between ground and unmanned aerial system measurements, for this first objective, we have measured several properties in recent years, looking specifically to remeasure diameter, breast height, the plot center locations, and the individual tree locations of specific trees. This is because we recognize that many of these properties haven't been visited in 8, 9, or 10 years, so we'd like to update their current size. For this coming research season, we'd also like to continue this remeasurement of specific attributes at the locations shown here, Woodman Farm, Moorfields, and Blue Hills. This is to make sure that there is a spatially contiguous distribution of inventory plots throughout the landscapes that we are studying. To confirm the presence of large trees for our second research objective, I'll be working with undergraduate technicians to locate, GPS mark, and remeasure the current DVHs of these large trees which have been identified. We will also assign a tree form class to each of these trees to later investigate the confusion which may be caused in the imagery from trees of varying canopy and stem structures. This tree form classification has 4 classes within it. The first one, A, is a single tree leading to one stem and one dominant canopy. The second classification shown here as B is a single tree with 2 stems forking above the DVH line, which still combines to join one canopy. For class C, there are 2 stems leading to 2 disjointed canopies. And for the final class D, this is a tree in which multiple stems lead to multiple To conduct a UAS data analysis, we first have to process the imagery into the high spatial resolution orthomosaics like we have in the previous chapters. This is using the structure for motion automated processing workflow. Once this data is collected, each of the individual trees will again be segmented or extracted. Once we have these crown areas and other crown dimensions, such as crown diameter, we can use a simple linear regression to estimate the diameter at breast height of the individual trees. With the variables such as diameter at breast height and tree locations, we can perform calculations for a number of stand and hectare level estimates such as basal area, stem density, and tree density. Throughout this process, we will also be measuring or generating confidence intervals for each of our estimations so that we may properly compare those to the forest inventory data collected on the ground. To determine the proficiency of unmanned aerial systems and their spatial models for observing large tree presence, we will also classify the segmented tree crowns as either large trees, because they meet that diameter estimation of over or equal to 40 centimeters, or small trees. With this classification, we will compare that agreement using error matrix to that of the forest inventory plot data using validated trees, which we have remeasured currently or recently on the ground. We will also be estimating the presence or abundance of large trees throughout both the stand and landscape level using the number of large trees which have been identified in the imagery. Finally, we will investigate the error or uncertainty in this classification further by using the multi-class classification, which was shown for the canopy form classes A through D, to decide or determine if a single or specific class shows heightened levels of uncertainty and should be further investigated. The final study infers an additional investigation that is necessary in our current climate: the ability of unmanned aerial systems for monitoring fine-scale forest change, stress, and disturbance. Forest pests and pathogens disturbances are highly publicized at the global and national levels, but are also very prevalent in our local environment. These forest diseases and pests they threaten ecosystem resilience, they reduce current and future ecosystem services, and are projected to increase under almost all estimations in the coming years. Most of the costs associated with managing and understanding these disease and pest distributions are a burden on local governments and private landowners. Urban forests, which we haven't defined yet, represent a keystone element in our global terrestrial ecosystem. These provide benefits which go far beyond those realized by urban dwellers. Urban forests can be defined as all trees located within an urban area. These provide benefits to global communities such as climate regulation, psychological and aesthetic value, and critical wildlife resources. While we'd like to investigate all of the species diversity which are available in our local ecosystems, we have recognized that there are 6 species groups which stand out as regionally important and face notable disturbances in our current climate. These are eastern white pine, eastern hemlock, American beech oaks such as red, white, and black oaks, ash trees, and red maple. Forest health represents a complex combination of vegetation and system traits. These include the physical environment and biotic processes, the ability of forests to be resilient to change and disturbance, a functional equilibrium between resource supply and demand, and having a diversity of stages and structures for forest stands. The vegetation responses to diseases and disturbances are diverse in nature across national, local, and even stand-specific scales. Trees can have individual and unique responses to pest and disease outbreaks. Monitoring forest health represents a number of challenges for today's conservationists and land managers. These include timing the observation for the specific disease outbreak or disturbance so that can be monitored effectively. The scale of measurements, whether those are at a state level outbreak, or I'm sure we'd like to all know right now what the local outbreak of certain viruses and diseases are. The costs associated with monitoring these, especially at a fine temporal resolution, and having an operational design for these, which can be implemented instead of having experimental results, which wouldn't be entirely practical. It is for this reason, like in our other chapters, we'd like to investigate the use of unmanned aerial systems for monitoring forest disturbance and stresses at a more local scale. To best support the detection and monitoring of changes in forest health, for this research specifically, we will determine the proficiency of unmanned aerial systems for classifying forest health at the stand, individual tree, and subcomponent levels. We will also calibrate a spectral response using the unmanned aerial system data for both healthy and degraded trees. And these are investigations across the 6 primary species groups which were included in the introduction. This research chapter specifically includes 8 woodland properties that were concurrently used in the previous studies. In addition to these, there are 2 urban environments and 1 natural environment which are not previously included. These urban environments include the Arnold Arboretum in Boston, which is shown here and is currently actually shut down as of yesterday, and the downtown Durham environment located here adjacent to campus. For the additional natural forests which we will include, there's the Walker Lot Town Forest in Bow, New Hampshire, which shows a heavy infestation of beech bark disease and other pests. To collect reference data on forest health, we employ 2 common sampling methods. We begin our investigations with the continuous forest inventory plot data, which shows us a silvicultural code or health of dead or dying trees. So we have a link to where to begin exploring the fields. For the 2 methodologies, we'll first use ocular guides on crown vigor, which are simple to implement and will provide a 5-class classification on the degradation state of specific trees. These ocular guide measurements can then be standardized and compared to remote sensing methods using a z-score estimation. The second methodology for collecting field data on forest health is by employing handheld spectrometers. In a lot of cases, these are devices which cost upwards of $90,000 to $100,000, but we couldn't quite get our hands on that for enough of the field season or expect other operational practices to do so. So we have 2 handheld link square devices, which are able to sense between 400 nanometers and 1050, so the blue through the near infrared light, and provide spectral reflectance graphs, which you see on the slide here. And these only cost a couple $100 as comparison. To best define the proficiency of UAS remote sensing data for observing forest health, we also evaluate traditional remote sensing imagery for the proficiency of classifying these degradation stages at the stand and individual tree levels. For traditional remote sensing imagery, we employ again the 2018 New Hampshire NATE imagery, which was available for the other studies, and now we also include Landsat 8 operational land imagery of these study areas. For the traditional remote sensing methods, we will apply 2 procedures for classifying forest health. The first one is a photo interpretation or image interpretation of these areas, in which we use the additional spectral bands, such as the near infrared shown in the below image, to visually interpret the degradation or health and disease class of individual sample units. For the second procedure, we will perform digital image processing in a supervised classification algorithm, most readily the best performing one from chapter 1, while also creating different vegetation differencing indices to perform that automated classification of the disease or degradation classes. For unmanned aerial systems data, for this research will be collected using the Sequoia Plus multispectral sensor. This is a 5-lens sensor about the size of a GoPro, which includes different lenses for green, red, near-infrared, and red-edge light, while also maintaining a natural color sensor in operation. We will perform the same structure for motion modeling that we have in the previous chapters to generate high resolution and now higher spectral resolution orthomosaic models. For much of this research, especially across the contiguous natural areas, we will be operating with the fixed-wing EV Plus and EVX platforms. For more logistically or legally constrained areas, we will also be operating with the DJI Inspire 2 quadcopter, which is shown on the screen there. This quadcopter is able to have a dual mount, which operates the Sequoia Plus multispectral lens. For this imagery, we will again perform 2 methodologies to classify crown vigor or health classes. These are first a visual interpretation or assessment, which matches that of the traditional remote sensing imagery. And secondly, we will again calculate band indices for these models and perform a digital image classification using the supervised classification, which performs the best. These classifications will first look at a binary class distinction in which they associate either healthy or dead and dying classes. If this performs well, we will also include a classification of the 5-level classification, which was originally designated using the ocular guides. Once these classifications are completed, we will also calculate a z-score so that we can statistically interpret the agreement between these various methodologies. So for evaluating the accuracy of unmanned aerial systems for classifying forest health classes, we will first use an error matrix to compare the binary classification, as I discussed, between the ground and UAS data. We will also do the same for the traditional remote sensing platforms and the ground data. Then we will provide that multi-class crown vigor quantification of agreement between the platforms. Combined with these analyses of thematic accuracy, we will also include that investigation using the z-score, which compares the interpretation agreement between the methods, much like the kappa analysis did in the original chapter. And then we will perform an exploratory spatial data analysis on both the models that were generated using these imagery and the classification process to determine the true uncertainty or sources of error which may occur during this type of mapping. This presented research represents years of compounding knowledge and refinement of methods, much of it stemming back to 2015. For chapters 1 and 2, we are largely underway with collecting that ground reference data, which is so vitally needed, and mapping the forest environments. For the 3rd chapter, due to some more, of course, logistical constraints and the availability of hardware, these methods are really going to be the focus of this upcoming summer. So the primary objective here is to collect as much data in this upcoming summer to hopefully have everything needed for analysis in the fall. We've, of course, learned a lot from flying these aircraft and platforms. We've crashed a number of systems and continue to do so. But with each successful or failure launch and landing, we learned something new about collecting this data and processing it. Before I can conclude, I'd like to thank all of those who've supported me throughout this research and my graduate career. None of this can be possible in isolation. Many of you have either directly contributed to collecting and interpreting data for me or helped me in the communication of it throughout the way. Of course, I have my basal lab members who are all here today, my committee members who are continually supportive and answer, even if I only email every other month or so. My funding sources, of course, which are shown there, the undergraduate researchers who have worked with me the last couple of years and continue to help out and make sure I know what I'm talking about. And then, of course, my family, friends, and loved ones, like my fiance and my dad, who are actually here, who make sure that I have somewhat of a work-life balance.
Just a little.
As much as I can allow. And with that, I'll leave you with one final image. I guess you can probably see that. This is taken high above the agriculture experiment station at Kingman Farm, just a couple miles away, and open the floor to any questions.
We need to take a couple of breaths now. We're tired of
Yeah.
listening.
Take a break.
Continuous. Excellent. Questions?